as I was a former organizer of this webinar. So thank you for the invitation. And today I'm going to talk about some results about uh, divergence-free G2 invariant G2 structures with divergence-free torsion tensor. I will try to present some results from my work with Eric Lubo, Enrique Saer, and Juliet Saavedra, and also some other results that I am preparing a preprint. I hope to finish at least next month, put in archive. So basically, the outline of the presentation will be in the first part some review about G2 structures. Maybe many people in the audience knows about that. It will help to fix some notation, and and also in order to explain our approach for the specific problems that we did. In the second part, I will explain the notion of isometric G2 structures, how they are related with a variational problem of, of specifically for a energy functional, and also the corresponding gradient flow for that functional. And in the last part, I will apply all the previous the previous items for the case of the Steven sphere and the case of almost abelian Lie groups, of course, for invariant G2 structures. So we start by considering the Doctrinal Algebra, which is a 8-dimensional algebra. We use the orthogonal split into the real and the imaginary part. We identified each component with one factor with air, and the other one is the imaginary part is identified with the 7-dimensional Euclidean space. And using the octonion product, the algebraic product, we can define an inner product as the real part of the algebraic, of the corresponding algebraic product for two elements in R7. And we can also define a cross product using the imaginary part of the above product. And using that structures given by the inner and the cross product, we define, in fact, it's an equivalence, but we will define the G2 group as the stabilizer of the free form phi0, which is essentially the inner obtained from the inner and the cross product above. And this free form phi0 is the canonical G2 structures in R7. So for a 7-dimensional manifold, a free form is called a G2 structure if there is a frame of the tangent bundle of M, should that you can identify at each point, you can identify the free form phi with the canonical G2 structure, phi0. Of course, that frame at the beginning is local, but if you think, for example, for homogeneous space of for Lie groups, as we will do here in this talk. Basically, you can define the G2 structures on the whole Lie group, for example, using the frame that trivializes the tangent bundle of a Lie group, which is the left or right multiplication, right? So essentially, this part of the definition, if you translate that to the Lie group, is essentially the way, for example, as Romina studied these SKT structures on nipotent Lie groups, for example. The important thing in manifolds with G2 structures is that you have all the Riemannian geometry is induced by the G2 structure by phi. Essentially, you can induce the Riemannian metric and the orientation using this formula. And of course, from the Riemannian metric and the orientation, you can define a Riemannian connection and also a hot-star operator and dual four-form psi. And we say that M, the manifold M with the G2 structure phi is a G2 manifold if the tree form is parallel with respect to the connection with the Riemannian connection induced by the G2 structure. That condition, of course, is equivalent with that the holonomy group, the connected component of the holonomy group, is contained in G2. That's why the name of G2 manifolds, right? And to obtain manifolds with that condition, with the holonomy contained in G2, Fernandez and Gray show that that is equivalent. It's equivalent with two conditions, that the G2 structure will be torsion free if and only if the phi is closed and psi is closed, which we call co-close, right? The close and the co-close condition. And if you see, the first equation is a nonlinear PDE, and the second couple of equations, one is a linear PDE and the other one is a nonlinear PDE. So in some sense, try to find examples of manifolds with torsion-free G2 structures is a difficult task. So in many problems, it's considered a relaxer condition for the G2 structures, as for example, just the close condition or just the close condition. The important thing in order to relax the torsion-free condition is that the intrinsic torsion nabla phi. I will in the next slides. I probably will drop the subindex, the index phi for the connection and the hot-star operator, but always we need to know that all that structures depends of phi, so in a nonlinear way. So the important thing here is that the intrinsic connection is completely described by the full torsion tensor T in coordinates is given in this way. This tensor is a tensor on it's an endomorphism of the tangent bundle of the manifold. So if you split if you consider the symmetric part of this endomorphism and the skew-symmetric part, you can describe your total torsion tensor T in 4 components given by the action of G2 on the endomorphism. The first 2, which involve tau 0, tau 3, correspond to the symmetric part, and tau 1, tau 2 correspond to the skew-symmetric part. And that components described for tau 0, tau 1, tau 2, and tau 3 are called the torsion forms, and they are defined by the exterior derivatives of phi and the exterior derivative of psi. So it was in fact marked by Karikianis that if you have a torsion-free condition, which means that the torsion tensor T vanishes, it means that each of one component vanishes because the representation is reducible for each one of that components. It means that each one of the torsion forms vanishes, which means exactly the equivalence of Fernandez and Gray, that the G2 structure is closed and co-closed. In fact, it was doing in a different with a different approach, but maybe using the torsion forms could be an easier way to see that with respect to the torsion, there are 16 classes of G2 structures with respect to intrinsic torsion. And in many problems in G2 geometry, they are considered some relaxed G2 structures. Well, in the first one we already see is the torsion free, the closed and the co-closed. The closed receive also the name of calibrated, and the co-closed also receive the name of co-calibrated because they are examples of calibrations in the sense of Harvey and Lawson calibrate geometries. But also there are some other interesting classes of G2 structures with torsion, which are nearly parallel. In particular, the Riemannian metric induced by this kind of G2 structures are Einstein metrics. Also, they are the locally conformal parallel, which means that if you do a conformal change of your metric, you obtain a parallel. If you do at least locally, you obtain a torsion-free G2 structure. And there are other ones, the purely co-closed, the locally conformal closed, and the locally conformal co-closed, which means they are the analog of the locally conformal parallel. So if you consider the 16 classes of the intrinsic torsion of the G2 structure, you have a way to stratify the space of G2 structures with respect to their torsion. But also they are another interesting way to study the whole space of G2 structures. How another way to stratify this space, and is using the isometric G2 structure, because we see at the beginning that if you have a G2 structure, you have an induced metric. So you say that two G2 structures are isometric, are called isometric if they induce the same metric and orientation. So in 2006, Brian showed, in fact, that you can parameterize all the family of isometric G2 structures using a scalar function and a vector field on M, satisfying so that that pair satisfies a unitary condition. And you say that you can construct a isometric class, which means the family of G2 structures with the same induced metric and orientation. And for this unitary condition, this pair F and X is identified with a section of RP7 bundle, right? Okay, and if you consider the case that your manifold is a homogeneous space with a reductive decomposition, and your G2 structure is invariant, if you consider just the isometric class of this invariant G2 structure, if you restrict this isometric class just to the invariant structures, this pair, the function needs to be a constant, and the vector field needs to be an invariant vector field. So, for example, for the case where the homogeneous space is the 7th sphere, and you consider the family of sp2 invariant G2 structures, we show that the isometric family of sp2 invariant G2 structures is parameterized by a section of RP3 bundle. Basically, for the condition that X needs to be an invariant vector field, you see that, of course, no always exist invariant vector fields, for example, in a homogeneous space. It depends of the composition of the isotope. It depends on the isotropy, right? But if, for example, if the isotropy has trivial representations, you will obtain invariant vector fields. And that's the case of the 7 spheres when you consider as the quotient of sp2 over sp1, right? You have 3 equivalents, 3 equivalents summands in the isotropy representation, and each one of them is trivial. It's a trivial representation. So basically, you can do the thing that we did for the 7th sphere, you can do for others homogeneous spaces with invariant G2 structure, and you can describe the isometric family, and probably will be obtained that your isometric family is also an RP3 bundle, or with S1 bundle. I don't know. It depends on the isotropy representation. But an open question in this for this result, on this, for example, for the 7th sphere, and of course for the case of the homogeneous space of a general homogeneous space, is if the restriction of the isometric class to the invariant structures represents the whole isometric class. It means that it means to ask if there is a non-invariant G2 structure inducing an invariant metric, for example. And of course, as we see in the previous slide, that the construction of the metric from the G2 structure is in a non-linear way. So maybe a direct answer to this question is maybe not possible, but we could try to use a different approach. And in fact, if you see that the pair f and x correspond with a section of a homogeneous bundle, and in the case, for example, in the case of homogeneous space, this homogeneous bundle M has an explicit uh, an explicit uh, an explicit form using an associated bundle, and we know that there are topological obstructions for the existence of global sections of the bundle M, which are the Stifel witness classes, in the sense that if one of the Stifel if one of the Stifel class is different from zero, so there cannot exist uh, the complement of the degree of global sections. So maybe one option could be try to compute characteristic classes for this kind of bundles, at least for the homogeneous case. Okay, so now with the
Andres,
using
can I just ask a real quick question?
yes.
So right, so the first your W1 is the one that detects paralleliz parallelizability, yeah? So
Uh,
right, so it's n plus 1 minus I global sections. Is this, yeah.
yes, yeah,
Sorry, I think that's right. I think that's right.
because I runs from 1 to 7, right? So
Yeah,
you can
yeah, that's
obtain.
right. Okay, it's good. It's good. All right.
Okay. Yeah, for example, so if we apply, for example, this approach for for example for the 7 sphere, and we compute the the four the four Stiffer Witness class, and we show that that is different from zero, so there are no invariant G2 structure in the isometric class, right?
Right. Interesting point. Yeah.
Okay. Uh, okay, so using this in fact we don't need we, we can define the energy of G2 structure in a sim in a natural way, which is the basically the L2 norm of the torsion associated to that G2 structure. The important thing here is that if we restrict the energy to the isometric class, and of course if we do an isometric variation of a given G2 structure, it means that that variation it corresponds with a time dependent pair f and x, a function and a vector field dependent of time dependent, with the initial condition which are equivalent with this initial condition for phi 0 equal to phi, and setting the vector field of the variation. You compute the first variation of the energy, and you obtain this formula, which basically describes the critical points of the energy functional. So the critical points for this energy restricted to the isometric class are the, the free divergence G2 structures, right? Divergence free G2 structures, where the divergence of the torsion, because the torsion is an endomorphism, so you can using the metric, you identify with a 2-0 tensor. So the divergence is a 1 tensor, which is essentially a 1 form given by this formula. So you can try to understand how this divergence of the torsion fits into the 16 classes of intrinsic torsion for a G2 structure. And Grigorian showed using octonionic section and some Dirac operators that the following classes of G2 structure with respect to the intrinsic torsion are divergence free. If you see the case 1, which is tau 0 constant, tau 0 initially is a function, but if that function is constant, tau 1 is 0 and the other two forms are arbitrary, that class is divergence free. In particular, for that case covers the classes of nearly parallel, closed, and purely co-closed G2 structures. And if your manifold is a homogeneous space with invariant co-closed G2 structure, because the torsion forms of an invariant G2 structure are also invariant, so tau 0 will be an invariant function, which means that it's a constant, and consequently you are in the first case of divergence free torsion tensor. And the second one corresponds with the locally conformal parallel G2 structure. And there are some examples, for example, in this kind of Lie algebras, parameterized by this kind of matrices. A former student of Jorge Lauret in Cordoba, in fact, constructed some invariant G2 structures with free divergence, with divergence-free torsion tensor. And in fact, that new examples are different from the classes that Grigorian show in his theorem. So this kind of manifolds with G2 structures are new examples of free divergence G2 structures. Okay, so now we consider the induced gradient flow for the energy functional. That flow has short time and uniqueness for the solution, because essentially it's a parabolic flow. But something important is that in fact you can describe the flow using sorry, here needs to be 1. I don't know what happened. You can describe your flow in terms of the pair given by the function and the vector field, and the gradient flow is translated with this system of PDE in terms of f and x. And if, for example, if you consider the case of homogeneous space, now it needs to be 1. I don't know why it's 3. But the gradient flow, if you restrict the gradient flow to invariant solutions, the PDE becomes an ODE. And if you set in the pair f and x, which in the case of homogeneous space is a constant and an invariant vector field, you can rewrite the couple of of equations that involve f and x just to one equation in terms of m, and here m times div of t means the octonionic product that I defined in the first slide. Basically, because you have for the derivative of f, you have the real part of the octonionic product, and for the derivative of x, you have the imaginary part of the product of n and divergence of t. The important thing here is that if you consider this last equation in terms of m, a very easy computation shows that the derivative of the norm of m is 0. So, in fact, when you consider an invariant solution for the gradient flow with the initial condition given by an invariant G2 structure, the flow, because of the equivalence between the pair f and x and the isometric G2 structure, the flow exists for all time.
Andrés,
Right?
can you just quickly recall what M is? So
Yeah, m is the pair f
oh,
and
M is the
x.
pair, right? Okay.
Yeah, and here we are in the invariant case. So one remark from this corollary that
But then,
if
sorry, still, how does the pair interact with div t? What is M div t? How do you operate this?
you operate by octonionic product,
I see. So, okay, so div t is well, it's a 7 vector,
yeah, it would be an imaginary octonion.
right? And okay, so you identify it with a pure imaginary, and then you make the product with M, which is an 8 vector, right?
Yeah, exactly.
Okay, cool.
Uh, and in particular for this corollary, if the solution, for example, is a self-similar solution, a G-invariant self-similar solution, uh, that the initial condition here we need phi 0. In fact, it needs to be a steady solidum, right? So for example, from this corollary, we obtain that in the invariant case, there are just steady solidum. There are no expanding or shrinking solidums. Some one natural question: if there are other solutions, if we can construct a solution for one particular case, for one particular homogeneous space, which is no self-similar solution, and that we did for the case of the 7 sphere. We in that case we consider one class uh, of isometric G2 of sp2 invariant isometric G2 structures that induce this invariant metric. Basically, this invariant metric is equivalent with the canonical variation of the normal metric, and we show that in the first part that the critical points of of for this class depends, of course, for the values of R. R here is positive value. That we show that for R equal to 1, hold the isometric whole the isometric class is divergence free. But if R is different from from one, sorry, we obtain two subfamilies of divergence free G2 structures in that isometric class. And we denote that family as a RP2 family and basically at 1 point in RP3. And one important thing is that if we consider a solution, we obtain a solution for the gradient flow with initial condition given by this isometric, with initial condition given in this isometric class, we show that we know, of course, from the previous result that the solution exists for all time, but we show that at the, in fact, that solution for this particular case converge to critical points of the energy to G2 structures with divergence free torsion tensor, and the behavior of the solution change from one stratification of the metric. If R is lower than 1, we have some behavior, but if R is different from 1, is larger than 1, we obtain the positive behavior.
So the point here is that the gradient flow lines in one regime flow from the equator to the poles of RP3, and in the other case they do the opposite thing.
Yeah, exactly.
Right, and this changes qualitatively at R equals 1.
Yeah, exactly.
Yeah.
Okay, so there are some other results involving the 7 sphere, but I think that results are the most interesting. In this case, we could describe divergence-free G2 structures with divergence-free torsion tensor using the isometric class. Using the isometric class because they are, in fact, they are a characterization for the invariant metrics for this homogeneous space. But for example, for the case of almost abelian, I don't know if there is. I didn't found a classification for the metrics, for the invariant metrics of this case. So the approach that we try to apply in this case was quite different. We try in this case to describe the free divergence, the G2 structure with free divergence torsion tensor using, in fact, the intrinsic torsion of the G2 structure. So I will define some things about this kind of Lie algebras in order to explain our approach. So we consider a 7-dimensional almost abelian Lie algebra which has a codimension-one Abelian ideal H, and we construct using the G2 structure and his dual form using the SU3 canonical structure for H, for the ideal H, which is Abelian. So basically, you identify with R6, the 6th dimensional Euclidean space. So it's the canonical structure for for C3. And so you have the omega, the fundamental form. You have from plus, which is the real part of the holomorphic volume form, the complex volume form, and rho minus, which is the imaginary part, and G is the complex structure, the canonical complex structure. And the important thing here is that these kind of Lie algebras are completely encoded by the Lie bracket is completely encoded by the matrix. The bracket is given this way, and using this bracket, you can compute the exterior derivatives for any K4 in G, essentially using that the exterior derivative of S E7, which is the orthogonal complement of the Abelian idea, is 0, and for any other form in H, K4 in H, the exterior derivative is given this way, where theta A of gamma is given by the canonical, is the infinitesimal action of the canonical action of endomorphins on forms. It's the pullback, the infinitesimal action of the pullback action. So the main the goal here is try to describe the divergence of the torsion in terms of the bracket, and try to characterize when the divergence of the torsion is 0 according with his relation with the bracket. These kind of things were doing for example, for Freiberg, in the case of in the case of almost Abelian Lie algebras, and he characterized in fact the closed and the co-closed G2 structures as some particular family of Lie algebras. Essentially, the Lie algebras show that the bracket is in this family of matrices, right? So our approach here was try to split the space of matrices GLH into the symmetric pair and the symmetric pair and the skew symmetric pair, and in each component we have a particular subspaces given by those that commute with J with the complex structure and those that anti-commute with the complex structure, as we describe here each of these spaces, right? So using this decomposition, we wrote the matrix A. Sorry, there twice, it's just one. We wrote the matrix for each one of that components, where S plus means the component in the symmetric part that commutes with J, S minus the symmetric part, of course, the traceless symmetric part that anti-commutes with J, and we say we did the same thing for the skew symmetric part. And using this description, okay, so one lemma before is that there was some quantity that appears in the computations that we did, is that this is this one form, which is a one form in H, and we show that this one form satisfies this identity when you do the contraction with the real part of the complex volume form. But the important thing here is that this one form vanishes if only if the skew-symmetric part of A that anti-commutes with the complex structure is 0. In the study in the case of almost abelian G2 structures with closed and co-closed G2 structures, this quantity alpha. Yeah.
Can I just ask you? So I think you're using the words commute and anti-commute sort of interchangeably, right? You want, so C minus are the guys who commute, right?
No, C minus are things that anti-commutes. Yeah, because
okay, so the
because
minus
for example,
anti-commutes and plus commutes.
Exactly.
Okay.
Yes.
Okay. All right.
This one for alpha, for example, for the case of closed and co-closed G2 structure doesn't appear because A, by definition, for example, in the closed case, A commutes with J because it is in this Lie algebra. And for the co-closed case, the skew-symmetric part commutes also with J. So
yeah, I confused it, right? Because there's in the anti-commutator there's a plus sign, and in the commutator there's a minus sign. It's on me. It's my fault.
Yeah, if you consider yeah, yes, yeah, exactly.
All right, go on. It's me.
Okay. Yeah, maybe it should be better to change the notation. Okay, so we have this important characterization for this one form alpha. Using the expression for the exterior derivative of phi and the exterior derivative of psi, we can describe the torsion forms in terms of the bracket. We have this description, in fact, using each of the components of the matrix A in terms of the symmetric part that commutes with J and the skew-symmetric part that anti-commutes with J. We did the same thing for the skew-symmetric part. And if you see something from these formulas, for example, if you are interested, for example, for Einstein metrics, there is a formula for the Ricci of almost abelian by Romina, and we see that the induced metric for an invariant G2 structure in an almost abelian Lie algebra cannot be Einstein if the contraction of the one torsion form, for the contraction of tau 1 with the element in the complement of the Abelian idea is 0, right? Because essentially the truss of the matrix is 0. So you can know in fact what classes of G2 structures on this almost abelian admits an induced metric, which is Einstein. And also you can see from these formulas that, sorry, here is tau 27 is essentially tau 3. It was a typo. But if you see that if tau 3, J of tau 3 is 0, immediately tau 0 is 0, right? So that shows that you can now obtain some classes of G2 structures with an intrinsic torsion. For example, you can now obtain nearly parallel nearly parallel G2 structures from in this kind of Lie algebras with invariant G2 structure. Of course, that obstruction is in fact it's a more general result that there are no nearly parallel G2 structures in these almost Abelian Lie algebras because the scalar curvature for a metric, for an Einstein metric in that case, should be positive if you write the scalar curvature in terms of the torsion forms. But we know that for a solved manifold, the scalar curvature is non-positive. So just the flat case is possible, the torsion-free case. Okay, but so using these torsion forms, we can describe the 16 classes of torsion of the 16 classes of G2 structures according to their intrinsic torsion. Basically, is this table, and we say that the G2 structure has some non-vanished torsion if the matrix, which is equivalent with the bracket, is in one of these subspaces, right? So using these expressions, we found what kind of G2 structures emit divergence-free torsion tensor. So basically, we compute the divergence of the total torsion tensor using the Levi-Civita induced by the left invariant metric, and we obtain this expression. If you see, this one is a one form, right? The first three elements are one forms in H, which depends of alpha, each of one, and the last term depends just for the trace of A and the trace of J times A. And if you remember, alpha vanishes if the skew symmetric part of A that anti-commutes with J is 0, right? And that space is that space is N, right? So if the matrix does have if the matrix have no M component, your the one for alpha is 0. And if we check in the table, basically just two classes, the 15 and the 16, have M component. The other classes vanishes. So for the other classes, the obstruction for the divergence-free condition of the torsion tensor is in the trace of A or in the trace of G A, right? So using that remark, we describe it's an analog of the theorem of Grigorian. We describe some classes of divergence torsion, divergence-free torsion tensor if the G2 structure belongs to one of the following torsion classes, right? Which is basically almost. We just didn't obtain any result for the class for the 13 and the 15 and the 16, which is with the whole torsion. But we see, for example, that if your G2 structure is of type 13, which means 13 means to have tau 0, tau 1, and tau 3 as torsion. It means just tau 2 vanishes. If we have that condition and divergence free, the G2 structure is of type 8 or 10. So in some sense, the free divergence condition for the total torsion improves your torsion, right? In fact, it means to have less torsion in the sense of the intrinsic torsion. And finally, we consider an example when A is in M. It means that the G2 structure is in the 15 class, right? And we construct an example where when this matrix is in fact the G2 structure associated with that almost abelian algebra is free divergence. So that's it. Thank you for your attention.
All right. I think we can take 5 minutes for questions. People have questions, comments?
I would like to know, Andrés, if you have analyzed some kind of existence of lattices in these almost abelian algebras, just to get to some compact examples.
No, I didn't, but yes, that would be an interesting question, because if you know, because in this case we obtain the examples of divergence free, right? Using the equation, using the Euler-Lagrange equation. But yeah, in order to define critical points of the functional, we need to obtain structures in the compact case. So that will be also an interesting question in order to study stability of that critical point. So
okay.
Something else.
Okay, good. Well, thank you. Very nice talk.
Thank you.
All right. Any more questions? Andres, maybe you can go to the last slide and just give some extra stress to your main conclusion, because I'm sure you know by heart all of these types 13 and 8, but I've only learned this 4 minutes ago. So maybe you can explain what's happening here. So if you start with maybe you can show us the table and explain us the theorem as we look at the table.
Yeah. For example, this kind of idea.
Can you show us the table?
Became from in fact it was with a discussion with Adrian some weeks ago, when we was studying the case of almost contact, and he showed me that there was a paper where they described the harmonic almost contact metric structures with the harmonic, which is the equivalent with the divergence free, right? In terms of the intrinsic torsion, So we did the same thing for this case, for the at least for a particular case of almost abelian. We can describe all the classes of intrinsic torsion, and if you see in all these classes, the n component just appear in the last two classes, right?
Yeah.
So the divergence free just depends from the class and the multiple of the identity and the multiple of J. So you need just to check for what classes one of that, at least one vanishes. And if you see that happen uh, almost everywhere, except for the case of 13 and 15, right? And of course for the whole class 16.
Sorry, can you say that again? So we see here the torsion forms which are not zero, right?
Yeah, exactly. The torsion forms
Right.
that are not zero.
Right. So you're saying if I have type 13, then tau 1, tau 0, tau 1, and tau 3 are not zero.
Are not zero,
Then,
exactly.
yeah, then unnecessarily type 8, oh, that's obvious, but type 10, right, this is just choosing 2 out of 3. So it's obviously true, but it has a geometric meaning, and that's the thing.
Yeah, the last, yeah, you see the one class, right? And you see the last column of the table, it's the bracket, and you have a formula for the divergence of the torsion in terms of the components of that bracket, which essentially is given by alpha and the trace of A and the trace of JA. But if you see alpha depends of the M component, right?
Yeah.
And you don't have M component in the 14.
Sure. Yeah, M is the reductive complement of SU3 inside the skew symmetric, right?
Yeah, exactly.
Right.
So you just need to see for the other classes when the matrix has a multiple of the identity or a multiple of J, right?
Yeah.
And you check case by case and you obtain, you see that, for example, in this case, in the 13, you can have both. So perhaps in this class, this class of G2 structure with this intrinsic torsion is not necessarily divergence free.
Correct.
But if you consider one G2 structure with this torsion and divergence free,
right, then either tau 1 dies or tau 0 dies.
Yeah, tau 0 or tau 1 dies.
Yeah.
So
interesting.
You improve your torsion to, for example, to the
right. I agree. You move up the table, and that's better than you had before. If you fit in another a more definite torsion class. Yeah, I agree.
Exactly.
Interesting. So even though in general the divergence free condition is I mean, it's not strictly related to the torsion classes. What you show is that in this case, it causes you to move up in the table. Right?
Yeah,
that's a fundamental remark, right? This tends to be some sort of transversal to the torsion classes, but in the almost abelian, it's not.
Yes, because the stratification of the space of classes G2 structure is given by the matrix. So yeah, you cannot fit the divergence free condition into one of these classes. Yeah, could be.
But in this case, you can, in a way. It forces it
Yeah,
to
in a
move
way,
up.
yeah, exactly.
I think it warrants a remark because this phenomenon is not general. And also a word from our sponsor. People in the audience can choose. I mean, do you prefer calling a G2 structure is saying that a G2 structure has a divergence-free full torsion tensor, or just calling it harmonic?
Yeah, sure. Yeah, but the people needs to know that harmonic is different from the definition of harmonic form using the Hodge Laplacian.
Oh, I see. Right. Yeah.
Because harmonic in the compact case is torsion free.
So the price of not knowing that is having to call it the divergence-free full torsion tensor G2 structure.
Yeah, that's why I choose to use.
I see.
Divergence.
All right. Well, that was a word from our sponsors.
Okay.
It's a free country. Still. All right. So shall we? Are there any more questions? Or can we thank Andrés again? Interesting talk.
Thank you.
All right. So we'll see each other in 2 weeks' time, and maybe the organizers could stay on for 5 minutes, and we could stop the recording now, I guess.
Okay.
Who's handling the recording? Paolo, are you who's handling the recording? Juliet, are you handling the recording? We need to stop recording. Stop recording. Hey, recording. Stop. Luis, are you handling the recording? Can you please make it stop?